So I'm Stansell, and I'm here to talk about PocketQube propulsion. Okay, so what you can actually see there is a picture of one of our thrusters, the Pocket Rocket, firing in vacuum. And really what I want to do with this talk is kind of break down some maybe mental barriers we have when we think, oh, PocketQubes can't have propulsion and the types of propulsion. And even I want to, go further and see if we can break down barriers when we think about propulsion in general. And one of the big things I want you guys to take away is that you can actually take the plumbing out of propulsion. So there we go. Yeah. So if we just think about the history of technology, right? So there's a lot of talk about, has technology stagnated, or is it rapidly advancing? And really, if you think about that, if we have something like plumbing, you know, at one point, having hot water and plumbing was actually cutting edge technology. But that has really not gone very far in even like the last 50 years or even the last 100 years. It's essentially the same thing. And then if you think about the technology that is rapidly advancing, that would be like semiconductors, PCB manufacturing, and chips. So the space business really demands propulsion, especially as we look to the next phase of space business and space exploration. So whether that's VLEO constellations for defense, whether that's orbital AI data compute, whether that's like going to the moon and Mars and creating space industry and even mining asteroids, all of that is going to require a lot of propulsion and a lot of delta V. So we have chemical propulsion. As you can see, you've got a nice Raptor 3 there. So it's very good, and you kind of need it to get into space. But once you're there, it really isn't the best option that we have. And so I put on the failure modes too many to list, and there's probably at least 1,000 videos that Scott Manley has that you can watch about the various ways chemical engines can fail, because there's so many moving parts, extremely reactive, like high pressures. So those really can't be miniaturized very much, and even on the largest satellites cause a lot of issues. Then we have electric propulsion. So electric propulsion is very cool because your specific impulse can be much, much higher, which is essentially your fuel efficiency. And the reason for that is that you unlink the acceleration mechanism from the propellant. So you're no longer limited by chemical reactions, where in a chemical engine, your maximum theoretical specific impulse is only about 470 seconds. You can go way, way higher. But the big problem with electric propulsion, as you can see up there, it's the Hall thruster. So if you take a look there, the actual thruster is just the part on the front, and that alone is relatively bulky itself, because you got the thrust assembly, the channel, the hollow cathode. But then if you look behind it, that's propellant tanks, like valves, flow, pressurization, all sort of things just to run that thrust in multiple power supplies. So yeah, that takes up a lot of space. Then we also have a noble gas problem. So if we're looking towards this future of bases on the moon, bases on Mars, huge giga constellations, not even mega constellations, you want to be able to get propellant from the space environment. So xenon is the best propellant for Hall thrusters that dominate. And as you can see, it's 0.09 parts, so it's 90 parts per billion in the atmosphere, right? So it's extremely rare. And that also means that it's very expensive, and it's also completely supply constrained. You can't just sort of mine xenon from the air. You have to liquefy a ridiculous amount, and then the supply, it's like a very inelastic supply chain for that, and the other noble gases. Krypton is slightly more common, but has less thrust. Then argon is much more common, on Earth at least, but it has the worst thrust out of the three. And if we look forwards to, based on the moon, based on Mars, you can see there, if you wanted to like mine some argon out of the Martian atmosphere, you'd have to process over 50,000 liters just to get 1 gram of argon. And I tell you guys a chemistry joke, but all the good ones are gone. Okay. Okay, so basically the bottom line is all these gas propellants, especially the noble gases, are very earthbound supply chain. and they have a lot of issues with them. Oop. So what if your propellant was a metal? And we can even go further. What if your propellant was any conductive solid? Now we're talking. Because in the space environment already, and if you just look at the periodic table, there's, it's dominated by metals. There's so many metals. And if you go to conductive solids as well, if you include carbon and carbonaceous materials, there's just a huge number of them that are conductive and actually could be used in a new type of thruster. And then you can see the advantage of this, especially with metal propellants. So what we have in the top there is a comparison with the equal impulse for two systems. And you can see that's in like a 3D CubeSat frame. But what you can basically see is that at the bottom we have metal propellant. And because it's so dense, we have the metal propellant there. We have the power processing unit. We have everything that we need. All of the control boards are in there and everything that you need to run the thruster. Then if you compare that to the top, it's taking up the entire 3U volume, and that's just the tank. There's no thruster in there. So even that you wouldn't be able to use. Cool, so how it works. So basically the technology we're working on at Solid State Propulsion is vacuum arc technology. And it sounds exactly like what it is. It's an arc in vacuum. And the key insight is that it's a low voltage, high current type of arc. And essentially what happens is you have this very microscopic region with insane physical parameters. So it's a region on one of the electrodes, the cathode, called the cathode spot. And that's between 10 and 100 micrometers. And within that region, even if the global circuit voltage that you're using is only 40 or 50 volts, you can have insane field and like essentially electric field and current densities that are like 10 to the 12 amps per square meter and like 10 to the 12 volts per square meter because it's constrained in such a small area. And so essentially what happens is on the global macroscopic scale, there's no high voltage, it's nothing too crazy. It's like a simple 40 or 50 volt supply. But then if you zoom in to the cathode spot, which you can see some images up there, it's an extremely violent and extremely like high pressure zone where you create an extremely dense plasma. And what's actually really cool about this is usually like if you're talking astrophysical plasmas or even lab-based plasmas, usually the plasma densities are nowhere near atmospheric because obviously atmospheric pressure is very high. But in a vacuum arc, the actual density of the plasma near the cathode spot actually approaches the density of the metal. So it can be even higher than atmospheric density. So it's an extremely high pressure region. Yeah, and basically, that's a lot of technical speak, but the takeaway is it allows us to take all the plumbing out of propulsion. And so we can generate very high velocity, violent and explosive plasma jets. Okay. Yes. Okay. Hacking delta V twice. Okay. So, we all love KSP. We all love getting more delta V. So the first hack to delta V, essentially, and delta V, obviously, it's the change in velocity you can impart to your spacecraft. So the first hack of delta V is basically the reason why we use electric propulsion. If we can make our exhaust velocity much higher, it's just right in the rocket equation, you get essentially an exponential increase in your delta V if you have a linear increase in exhaust velocity. So everyone knows about that one, and that's a huge unlock. And that's why most satellites use electric propulsion, because you can get so much more out of the fuel that you have. So that's the first hack. And you can see that, yeah, vacuum arc thrusters like this can get over 1,000 seconds of ISP, which is much, much higher. And then the second hack is that if we can extract some of these fuels in the future from the space environment, then we're no longer paying this delta V cost of taking all of our fuel from the gravity well of Earth. And then this is the second huge unlock, is that we can get even more delta V because we could essentially launch spacecraft and then rendezvous with easily, near Earth asteroids or easily retrievable space debris, metals, this type of thing, which is a huge unlock in terms of even more delta V. And just a quick note on that, we did actually test a real metallic meteorite in the thruster, and it performed almost exactly the same as pure metal. So that was really cool. Yeah, so all of this leads us to the key insight about vacuum arc technology is that it's about scale. So because the plasma creation process is microscopic, it means there is no limit fundamentally on how small we can make these propulsion systems and still get really efficient performance. So if you compare that to gridded ion thrusters, Hall effect thrusters, um, inductive energy, plasma creation thrusters, all of those systems have basically requirements on magnetic and electric fields that make it physically basically almost impossible to miniaturize them down to the pocket cube scale and below, because you need a certain magnetic field strength to get efficient ionization of the plasma. But because we have the ionization of the plasma happening in microscopic regions, you could theoretically make. Great. So PocketQubes, that's why we're here. So PocketQubes are really in an exciting time. I think, I was here at this conference 2 years back, and it's really cool to see how, it's grown. And again, thanks to Elbow Orbital for, always having this such a cool meeting place for this cool research. And there's some really interesting talks and really interesting research that's been happening. And what's exciting about PocketQubes is they're still at the cutting edge, and maybe in some ways even more at the cutting edge, because they have all these constraints and because the risk tolerance is much higher because they're lower cost. So many interesting things are happening. And basically, you know, what's really exciting is that they're kind of going from this phase of experimentation and projects into serious commercial platforms that have. So yeah, I mean, if you haven't been listening, then this is a good slide for you. But essentially, you can't use traditional electric or chemical propulsion systems on PocketQubes, just because, yeah, there's a lot of reasons already that I mentioned. Another one is that if you want to use a ride share, even on a CubeSat or a PocketQube, there's extremely stringent requirements on anything pressurized, any liquids or gases you have, anything reactive. There's huge requirements on that, obviously, because you can imagine if you had some like small chemical, like hydrazine mono biprop or something, and then somehow something goes wrong with that, your small rideshare pocket cube could jeopardize, like an entire launch. So that's why there's very strict requirements. And then again, with the traditional electric propulsion, you need to generate the plasma somehow, and every other method needs essentially complex feed systems and these larger things that simply can't fit. So that brings us to solid pulse. So solid pulse is the evolution of pocket rocket, and it is our latest thruster. And you guys, let's go take a look at it downstairs. We have an engineering model doing nice slow rotation in the display there. And it essentially just gives all of these advantages. So it's fully solid state. There's also zero warm-up time. And we've also designed and made advances in the power and the electrodes so that it's very low power operation, and because it's a pulse system, and there is a video you'll see in a bit, you can really vary the input power to whatever power budget you have. So you can run the thrust at 1 watt, and it will have the same efficiency, same thrust to power, same ISP than if you ran it at 100 watts. Yeah, okay, cool. So there's a video of one of the flight models firing in vacuum. And another great thing about the solid pulse, especially if you see the unit downstairs, it really is, we're trying to make some jargon here. It's a software-defined thruster. So everyone knows about software-defined radios, other things are software-defined. So what's really cool about solid pulse is because the thruster and like the electrodes are essentially an electronic component. There's no valves, there's no feed systems like that. It's essentially fully electric. That means that we have a huge amount of control over the voltage levels, the current levels, everything that we feed into the thruster. And then going beyond that, we've designed it with full redundancy. So we could lose, one part of the thruster, we could lose a boost converter, we could lose a microcontroller, and everything is cross-strapped. So, and you can see it's still in a very small package that's downstairs, but we can reroute essentially the path so you can always produce thrust. Yeah, and then another thing with PocketQubes is, actually, yeah, a lot of people don't know this, but basically PocketQubes are actually the draggiest of satellites, especially when they have deployables. So even though they're very small, the cross-sectional area is quite small, but because they're so low mass, the ballistic coefficient's really bad. So out of pretty much all PocketQubes out there, they're extremely draggy. And I know Tom is always posting on LinkedIn, like, when a unicorn deorbits, and sometimes it's as little as like 280 days because they're quite draggy. So that's a big issue. And yeah, essentially, so done detailed calculations, essentially showing that for like a 3P or a 6P mission, if you just add one solid pulse unit, you can guarantee over 3 years of lifetime. And if you don't have any propulsion, then your satellite will likely deorbit in roughly 280 days, depending on the drag and solar activity. Yeah, so that's just a bit more about that. So it's essentially guaranteed over 3 years with 1 unit on current performance, and then you can get, push that all the way to 10 units with 2 units, and that's at least 4 times the lifetime of a typical PocketQube. Yeah, so then we also have a European Space Agency dedicated in-orbit demonstration happening next year. We're very excited about. And yeah, there was also, like, it was great timing because both talks, or even 3 talks right before, were all about, essentially precise orbit determination with the retroreflectors and other methods, which is very cool. And what's also great about this IOD mission, we're working with a team. The satellite's going to be called Electra, and they are measuring ionospheric electron content, and they're using basically two phases of the GNSS signals, and they use a Doppler shift for that, and that allows them to very precisely measure their science mission, which is the ionospheric total electron content. But then at the same time, that enables extremely precise orbit determination. So yeah, you must contact them if you want more information. But they've told us that they should have, like, on the order of 1 centimeter precision in terms of positioning, which will be great to see and validate exactly how the thruster performs. Yeah, and there's a picture of the team and a little bit more about the precise orbit determination. So sort of coming to the end here, before we go to lunch, I know everyone's excited. Essentially, what does this unlock? So I really believe that having reliable, proven, high-performance propulsion on PocketQubes really unlocks them from this level that they're currently at, which is still very exciting, but somewhat limited in many ways. And it unlocks them to becoming the fully fledged satellites that we all know they can be. And so whether that could be VLEO constellations, Earth observation, even things in higher orbit, it really just enables a lot more possibilities that are very exciting. Yeah, and then the bigger picture is also we want to make propulsion systems for all sizes of satellites using this technology. So this is just a starting point, but we're very excited about it. And yeah, the longer term vision is that we can radically have, essentially, yeah, if we go back to the start of the talk, we think about technologies advancing. Plumbing really hasn't changed very much. So if you want rapid iteration, you want rapid launch of satellites, rapid manufacturing, and then you want very tight tolerances on those systems so they can all perform. That's something that with almost any other propulsion system, you have a lot of challenges with because it's very bespoke and there's a lot of essentially plumbing involved. And if we can take that into the 21st century and essentially make propulsion systems completely solid state, like we make transistors, then I think that's really a game changer for space travel and exploration. Yeah, so thank you for your time. There's my contact. Good.